Hey guys, Max here, and yeah, it's been a while. I haven't posted a video. So, yeah, there was like a lot of things were going on. I uploaded my last open source project, OpenNeutron, but unfortunately it didn't gain any popularity. I mean, not popularity, it just got a couple of stars on GitHub and that's it. So I haven't actually received any proper feedback other than Proton Mail, guarantees and whatever. So I mean, yeah, if they guarantee, you probably know what they're running on their servers, do you? So why do you even bother? But whatever. Yeah. I saw in one of my previous streams a stream where I was writing my own hypervisor gained a bunch of views, and this topic is of particular interest also for me personally because I don't know, I just love the virtualization stuff, and I was always dreaming on about writing my own hypervisor, right? And I mean like type 1 hypervisor. So yeah, I experimented for quite a while with QEMU and the Proxmox like hypervisors, because with all the respect, people who are comparing the Proxmox to the KVM, it's just the most stupid thing ever, because Proxmox is basically a KVM. Proxmox is, well, just a smart um well overlay for a smart graphical user interface for the KVM, basically running QEMU commands itself. It just spawns the QEMU threads, right? So there's nothing complicated about that. And we did certain things, we did similar things on our own with me and my colleagues. Actually, one or two times I did it live on the stream. So yeah, but I wanted to go actually deeper and understand how everything works, right? Because there are a lot of problems with a KVM. First of all, I mean, it's Linux. With all the respect to Linux, say, well, I'm using Linux myself, but this thing is bloated, and I had quite an experience writing drivers for Linux. Mostly at the university. Actually, we wrote some exploits, exploits, custom drivers, whatever. So I know what's going on in the kernel, or at least I pretend to, and I got a feeling I somewhat know what's going on there. But the thing is, the kernels is very old. It's bloated. It kind of gives this bloated, over bloated feeling, right? There's no proper development kit there. You have to dig through like tons of documentations and kernel header files, specifications. I mean, that's all right. And if you know what you're doing, you're probably gonna achieve the goals. But again, that kind of felt off, and I was trying to like start digging on what other virtualization techniques, virtualization systems there are, and there aren't much. So we have the virtualization king, which is the Hyper-V. Well, that's not a king. Sorry, I mean the XenV, which was one of the first virtualization platforms we even got. So that's basically a gold standard. For some reason, it's not being used quite that often anymore for whatever reason. Because I guess because KVM shows better support or has larger community. That's alright. All right, don't have a problem with that. Well, we have the Hyper-V, which is a Microsoft hypervisor, and with all the respect, I mean, well, I don't have any respect to Microsoft, I gotta admit, but Microsoft and the word Microsoft and word good or at least decent software, they cannot even be in one sentence together, right? So Hyper-V, I mean, like, what the hell is that? Yeah, they made themselves large with all these government contracts and God knows what. But you don't actually, first of all, Microsoft and performance, come on, guys. Even stripping all the bloated AI shitware, that's not gonna perform well. We all know that. Come on, let's stop pretending, all right? And yeah, so this is a proprietary stuff, right? And yeah, we don't actually know what's going on there. And yeah, you gotta pay for it, obviously. And we have last but not least, it's the ESXi, which is for on the one hand, it's a pretty much nearly a gold standard as well. It's very good. It's high performant. It's enterprise ready, but it's small. It barely has any footprint. It has memory footprint. I mean, it has awesome support. It has live migrations, everything you can possibly dream of. But it's proprietary, and with the new Broadcom acquiring the VMware, I believe the licensing got even stricter. So yeah, we have any as an open source community, we don't have any much options other than using Linux, either flavored by the KVM and used by the KVM, and or with the with Xen, so with the Xen hypervisor. So there aren't any things we could do there other than, well, maybe we could do something on our own, can we? That's what I thought, and I started digging. And at the university, our operating systems professor, and I visited him during my first lecture on the most basic operating system. So I told him, Professor, well, we have this and that, this, and I laugh. Well, I'm trying to understand really understand the virtualization. So, maybe you would, well, uh, explain me, or at least where to look for the information, because as you probably noticed, if you Google like virtualization or how to write or how to create a hypervisor, you get like 20 videos, professionally shot videos in some fancy home labs where guys are basically talking the same thing, that there's type 1 and there's type 2 virtualization, and giving some examples, and that's it. So no one goes actually deeper into how this thing actually works, and that's what I was trying to figure out. So yeah, I came back to my basically that was one of my childhood dreams. I gotta admit, write my own operating system, but since it's not actually of any use, I decided somehow I moved for like 3 or 4 years ago, I slightly moved to the, well, my dream is to write my own hypervisor, my own type 1 or type 0 or type 1, type 1 is it? It is a hypervisor. So yeah, and at the university I was told, well, there's a thing called Sal4. Maybe take a look at it. It's a kernel. It's very small. It's a microkernel. But it's VM capable. You can run VMs with the help of it. You can. And I was thinking, oh yeah, maybe I should really take a look at it. And this is where I landed. Couple years after this discussion, this is where I landed. I took a look at the Sal 4, and yeah, I decided, so let's go. Let's write our own hypervisor based on Sal 4. Now, in case somebody does not know what a Sal 4 is, it's a microkernel, and the nicest thing is first of all, it's a pretty modern one, so it doesn't have the legacy shit a normal kernel would have. Well, again, it's a microkernel, so it doesn't have any drivers. It only does the most basic memory stuff. And the third thing, which is like the most awesome thing, is this is one of the first kernels, I think it's even the first open source kernel, which is completely formally verified. So it has a mathematical proof, and it's certified to be used in the defense and aerospace, and uh, God knows what other industries where nothing could go wrong. So it just does not break. All the memory is completely verified. So inside the kernel, nothing could even theoretically break, and that's I mean, assuming the hardware is working as intended, right? But if the hardware is new and works perfectly, then nothing could mathematically possible break. So, this is why, and so I didn't want to write the kernel from scratch, because it would require like a lot of time, and useless thing, like a not interesting thing, like for example, programming an Apex advanced programmable interrupt controller, and writing all these stops, and debugging, and yeah, that would be just way too complicated. And for x86 we have to implement the mode switches. Well, yeah, they can be implemented, and we have them implemented here, but doing all this thing manually, it's just a lot of copy paste assembly, like, and there are a lot of things I would miss out. So again, I decided, like, let's go with this kernel. It basically has all the toolkit we need, and on top of that, let's, well, write a goddamn hypervisor. So that's what I did. And yeah, this is the main function. And as you've probably mentioned, this is a Rust. Yes, there's a native or nearly native development kit in Rust. And the on the one hand, for me it was pretty disturbing, but on the other hand, very cool, really cool thing was, um, I'm writing my own. It was nearly as writing my own operating system, but in a user mode. So, sorry, let me explain a bit more. The thing is, first thing first, the cell4 kernel does not have proper memory management, meaning it does not have an allocator. Why? Well, because it's not verifiable. An allocator, well, can any piece of software could, like, at any time ask for whatever memory, and having a memory allocator in the kernel would make it unverifiable mathematically, so they just didn't add it. So you might ask, how then we manage the memory? Well, and that's the point. We have to manage it on our own from the user space, right? And that's, again, so we are basically a kernel while running in a user mode and telling exactly the kernel what to do. For example, we have physical, it is actually nearly one-to-one mapping. So we have untapped regions, we have a physical allocators here. So, but don't forget, again, it's a damn user space, right? So, yeah, I had to type a lot of comments here, and some of them were a bit modified and by the AI, not gonna lie. Sometimes I'm using AI for testing, for writing automatic tests. It makes things much easier. Or sometimes to help me out with some Rust syntax or Rust borrow checkers. I don't want to file them, I want to understand them. So yeah, again, I am not against using it, but I'm pretty much against vibe coding. Please, there's a lot of difference between using it and vibe coding it. So yeah, here we have our frames, and we are basically, right, telling the they're so-called object blueprints, right? So we are basically telling and allocating the memory. All right, so yeah, we're telling the kernel what to do. All right, so that's pretty strange. But the thing is, we as a main process, actually we get ourselves all the memory, and we just tell the kernel first to map it, and then we can partially distribute it. So yeah, then we expand C node. Again, the cell4 works totally different from Linux. It has so-called C nodes. It has so-called capabilities. to store basically objects. Everything's an object here. So yeah, here for example, yeah, we gotta put info pointers. So we're a root task here, and we have certain rights. It has a very strict rights separation, right? So yeah, and here we have a TCP. Here we're basically expanding the so-called, well, um, C nodes, well, objects, and there's certain amount of how much we could fit them, and we can sometimes under certain conditions, well, we have enough resources here. Again, don't forget this kernel is actually meant for embedded devices for aerospace or whatever industry, right? That we're running it here on PCs. It's not quite what this thing was designed for, but yeah, so, and we're basically expanding these so-called capabilities, expanding this expanding the C nodes, the amount of C nodes and the C node is, for example, a page descriptor, a memory page descriptor. So if we want to fetch more or use more memory, we gotta have more C nodes, so we could fit the page descriptors in there. Again, if someone is a Self or Pro, please. I'm really sorry. This code is by far not optimal. It's the first time I did something like this, especially in Self 4. So if you got any remarks, you're free to comment, and I'm gonna try to fix them. It's the first time I'm doing something like this. So yeah, and so we're here when we are initiating the guest memory. So a guest memory, guest memory. There's also a so-called, well, there's a my custom-made wrapper for the for managing the guest memory. So you can see the slot for the space, the base, the size, everything we gotta know basically. And there's a so-called level 2 page, I believe it is stage 2, I think it's called, yeah. So we take ourselves some memory, we allocate ourselves some memory, and then we basically tell the MMU, well, there's actually this certain memory region is actually a virtual machine memory. So let's write it. As you can see, VM attributes. We map a frame, right? And yeah, so please, well, we have to mark this certain region as VM, well, runnable, so that this thing contains the virtual machine. This is basically a virtual machine memory, yeah. So in this case, we're basically allocating 100 megabytes of this thing. Yeah, I guess RAM size we have here, as you can see, 100 megs, and later we are yeah, we're printing and we're loading the guests. So we have this the memory pointer, right? And we are writing, as you can see, we have here include bytes. It's just, this thing's awesome, this macros. So we're basically reading the direct bytes during the compile time, which is hard code the bytes here of our image, virtual device tree binary, and the CPIO, the rulefs CPIO. Yeah, which the initial RAM file system's gotta be fixed a bit later, but it doesn't work quite well. But that's the question of time. We're gonna figure it out a bit later. So we are loading. So you can see we are loading the to the guest memory. We are loading the first of all, we're loading the device tree binary, right? So because this is pretty much this were very similar to ACPI tables in x86 Advanced Control Power Interface, I believe it's called. In some, yeah, forgot to mention, the L4 does not have a proper support for x86, so I decided, well, also the market for the for x86 virtualization is bloated. It's that's basically it. We cannot actually, I won't be able to get through all the compares there and etc. So I decided to work on ARM. Yeah, so yep, we are this hypervisor is an ARM. It's an ARM hypervisor. I'm gonna be porting it to the RISC-V a bit later, which is a bit different, which doesn't have quite that many differences, but the ARM, it's a pretty much hardened. It has a hardened virtualization documentation, and the RISC-V is still more of a Wild West. We're gonna deal with it a bit later. And yeah, there aren't actually any decent high-speed hypervisors for well, for ARM and for RISC-V. Well, there are Zen. They are there is a well, KVM and Proxmox. I don't know whether it has a decent support. And there is an ESXi, and ESXi is, well, it doesn't, the ESXi is closed source, so that this is out for I mean, for home labs, etc. That it could cost some money, so this thing we don't consider. Also, the ESXi doesn't have a proper support, and again, the Zen and KVM, they're heavily relying on Linux, and they have a huge attack surface, which in my case I don't have. And in this case, we have like a tiniest possible footprint. I calculated it's gonna be up to 100 megs. Now it's actually 20 megs, but it's gonna be a bit more than that with all the virtual device emulation, etc. So it's gonna be more than that. So we calculate it's gonna be up to 100 megs of device well, memory footprint, and yeah, so, and it's not gonna have nearly as huge attack surface as other Linux dependent hypervisors. So yeah, let's continue. So here we're just writing the kernel. Here, yeah, we're reading the kernel, trying that it's gonna have magic. So yeah, this magic number, and yeah, we're just inserting the kernel at well, at the spaces here, and we are acting as our own bootloader basically. But later I'm gonna add the UEFI, the virtual UEFI. I'm gonna add it later, but now we're just booting it manually. Not a big deal. Oh, here I tested some threads, multi-threading, and the funny thing was, when I just started, thread was one of the first things I tried to do, and I got an error, and I was thinking like, why the hell? What is this memory error again? And you don't get actually I mean, you could get decent errors, but most of that time you see just a crash stack, and yeah, well, the process doesn't have enough space, and I was thinking like, all right, but doesn't it like allocate some space while creating process? And I looked it up, and now we have to, well, we have to create heap, we have to create stack for the process, and we just have to go with it, because we're just allocated ourselves, right? And we will fill a so-called TCB thread control block to the and we will fill it out ourselves. We are fully in control of this thing, and yeah, this is pretty much what it looks like. Well, there's this trampoline for the IPC communication. I really had to figure it out how it works, because it's a total different thing as it is in Linux, the inter-process communication. So yeah, use space. We have some virtual space here. I also have some allocations going on. So nothing that complicated. You just gotta figure it out. All right, but yeah. So and then we got a TCB, the thread control block, right? And we just push it to the execution. I mean, to the execution queue. We just tell the self-for kernel, well, there's a thread control block, and you would you kindly run it, and the rest we don't care. And that's a pretty nice trade-off because we have a lot of control. Well, there are a lot of things which could go wrong, and there are a lot of things you gotta know. But yeah. Um, if you know what you're doing or you're learning, it's you gotta figure it out one way or another. So yeah, and at the end, this expansive node. All right, so yeah, we are passing through some UART. So we have the console here. We're passing through the console, the serial console to the directly to the Linux kernel. And yeah, here we create a virtual CPU and a VM thread. Let me show you briefly how it works. I mean, what it looks like. There's this vCPU. All right, so a vCPU just has this memory, right? Because it gotta know on which memory region it runs and where it's isolated in, right? And this the slots and all the other important things. Yeah, the program counter obviously we gotta know. And actually, the main thing is the VM thread, and this is the most awesome thing in the self-for universe, at least what from my perspective now. Maybe again, I'm by far not a pro. This is just like a test and see what's how it generally works. As you can see, we have a virtual CPU object here stored. We have a handler here, which is a normal thread, which is just a thread I've just shown you. So the thing is, when a thread, you could just tell it to go to the switch to the VM mode, and don't care about it. And the next thing, and then the CPU is gonna be switched into the VM mode, and it's gonna be scheduled like a normal thread. So basically, what you can do is you can because this thing is obviously preemptive, right? You could create like 1,000 VM CPU threads, and you're technically you're gonna have like 1,000 CPU cores. Well, does it increase the performance? No, I don't think so. Actually, I think it slightly decreases it because of all the context switches, right? But is it technically possible? Yes. So you don't have the fixed binding you don't have the fixed binding to the of the virtual core to the real core. A virtual core is nothing but just a thread which is just normally scheduled, and that's awesome. It's spared me a lot of time in here. Actually, you see, this is basically a loop, and we are waiting waiting for the well, we are waiting here for the code to for the VM to exit. So there are certain well, scenarios where it exits. Well, it is running a guest VM, and for example, a guest VM wants to access some memory it doesn't have access to, or it raises some fault, or it I don't know, requires a CPU ID instruction, or tries to execute something dangerous, we might want to be aware of. And this is the second where CPU thinks, oh, well, wait a second, let me first consult the hypervisor, what hypervisor allows you to do and what's not, and it switches back to the hypervisor mode. So here it loads the vCPUs here, as you can see, the guest TCB and vCPU. Yeah, well, it's unsafe, but nothing we can do about it here now. And we're just waiting for the kernel to for the self-for kernel to give us what's happened in the virtual machine. Otherwise, we actually don't care. We'll let the virtual machine just normally run as it does, and we just don't touch it. And so we just gotta wake up the hypervisor when something happens, or in some interrupt, or I mean, yeah, we can actually inject the interrupts ourselves into the into the virtual machine, but again, that we don't care about it for now. And this was actually one of the hardest parts here, which well, we have to decode what's going on here and what happened, what not. And yeah, here I really uh, asked the AI to give me all these tables of all these addresses because it was just a nightmare. Again, not gonna lie, here I used the AI to make me all these tables and all these small things to just to quickly scout through the documentation, because again, it's just as you can see, any wrong bit here is it's gonna be nightmare to debug, etc. So again, in this case, not gonna lie, but at the end it worked. And yes, we can manipulate the registers, the context here. Yeah. So, and you might think, well, what does it actually work, and what does it look like? And the answer is yes, it does work. It perfectly works. I mean, it's not perfectly yet, but it works. It can run a VM. So it boots up. Voila. So first things first. Yeah, I tried it first with the Fibonacci numbers and just which I made raising some exceptions, and they work. And then I moved to actually loading the Linux kernel into this thing. So yeah. So we get our to the power of 22 slots for object for mostly for the page tables, right? Kernel. Then we are placing all these things over here. The kernel, the device tree blob, kernel, and the initial RAM file system. We're enabling the device's pass-throughs. In this case, it's just the serial port, serial monitor, right? And yep, map device, guest start, parking the root tasks, and this is the last basically thing before VMM starts. So yeah, so the thread starts. We're here just constantly in a blocked mode, but parking a root task. So this starts the VM and instantly like prints this thing, and yeah, but at this moment, as you can see, VM thread new it, and it launches the thread, and instantly we see booting Linux on physical CPU. Yeah, Linux thinks it's a physical CPU, as it should actually. And yeah, I compile it from the what are this it's called tiny boot, isn't it? Yeah, so I compile this like minimal kernel with an output to the serial monitor, and as you can see, it boots just fine, right? So yeah, some ranges. Print K works, everything works here, except oh yeah, it sure works. So yeah, it sees all the it detects all the memory. That's exactly 100 megabytes of memory we have given it. So yeah, and at the end it well, it fails because because yeah, the initial RAM file system is a bit broken yet. I'll have to figure out what's going on here and why, but that's kind of broken here, so we're just kernel panicking here. But the kernel itself is loaded, so this is exactly the output we're waiting here. And yeah, as you can see, it's a reboot failed. Yeah, because we don't have actually a hardware emulated to run the reboot, but there's another thing I'm gonna take care of. But yeah. So yeah, that's basically it. Holy shit, this video is like 34 minutes long. So yeah, I'm sorry for such long video, and yeah, maybe I was talking too much and showing too little, but I'm just really damn excited. So uh again, thanks for watching, and please comment, like, and subscribe. And if you want to see more on OS stuff and on hypervisor development, please let me know in the comments. And have a nice day.